All right, guys, good afternoon. So this is how to do number 10 on the chapter 5 review. A lot of people were having questions about that, and we didn't have a chance to go over it in class, so let's go over it now. Okay, so number 10. We didn't have a chance to go over the entire thing in class. So we got 6-liter sample of benzene gas at 30 degrees Celsius and 755 torrs combined with 12-liter sample of gas of oxygen gas at 23 degrees Celsius and 830 torrs. So here's the stuff we need. Right, we have the volume, the temperature, and the pressure for each one, which means that if we use PV equals nRT, we can find the moles of each one. So the first thing I would do is probably write the reaction out. So the reaction for number 10 would be 2C6H6 plus 15O2 reacts to form 12CO2 plus 6H2O. So it's combustion, which means it's always carbon dioxide and water, and then you just have to add the stoichiometric coefficients to balance out the different carbons and stuff. And so the first one for benzene, you would convert the torr that it gives you in the problem, which is 755 torr, to ATM, and that would be 0.9934 ATM times its volume, which was 6.00 liters, equals moles N times 0.08206 liter ATM per mole Kelvin, times the torr, or times the Kelvin temperature, which converting 30 Celsius to Kelvin is 303 Kelvin. And when you solve for moles, you get the number of moles is 0.2397 moles of C6H6. So we do the same thing for oxygen, and its pressure is different. So when you convert that to atmospheres, you get 1.092 ATM and 12.00 liters. It gave you and then N, and then the same 0.08206 liter ATM per mole Kelvin, and its Kelvin temperature was a little bit lower. It was 296 Kelvin. So when you solve for moles in this one, you get 0.5394 moles of O2. Now it would seem like the limiting reactant here is the benzene because there's fewer moles of it, but we don't have quite that simple because only 2 moles of benzene are used for every 15 moles of oxygen. So one of the ways you can find which one's the limiting reactant is convert each of these to moles of a product and see how much of the product is made. So if we convert the benzene to a product, we got 0.2397 moles of C6H6. We'll convert that from moles of C6H6 to moles of like carbon dioxide. We can pick whichever product we want, so let's do that to moles of carbon dioxide, moles of CO2. So in the problem, 2 moles of C6H6 goes into making 12 moles of carbon dioxide. When we convert that, we get 1.4382 moles of carbon dioxide can be made from our moles of benzene. So that's the maximum that can be made if all the benzene gets used up. Now I have to do the same thing for oxygen, so using oxygen's number of moles, 0.5394 moles of O2, convert that from moles of oxygen to moles of carbon dioxide so that we can compare the two numbers. And we find from the stoichiometric coefficients, 15 moles of oxygen go into making 12 moles of carbon dioxide, 15 to 12. And so for that number, we get 0.43152 moles of CO2, which is substantially lower than this number. So that means that the oxygen, is the limiting reagent because it can make less product. So this is not how much we will make, this is how much we will make. So the next thing I should do is I should figure out how many moles of each of the products I made. So I should now take the same moles of oxygen because it's the limiting reagent, two different words for the same thing, and convert it to moles of the other product, which is water. So 15 moles of oxygen goes into making 6 moles of water. And when we calculate this, we get 0.21576 moles of water. So now we have the moles of carbon dioxide and the moles of water vapor. When you combust something, right, you're not making liquid water, you're making water gas. We're only making gases here. You can know this because this is a liquid. You can know this because when you burn something, right, you don't see a whole bunch of water vapor created. It's not like droplets of water come out of the top. You just see gases created, right? Things burn and gases come off of them. So we're forming both carbon dioxide gas and water vapor gas, which can exist in the air to a large degree, even at room temperature. That's the relative humidity thing. Okay, so all of this we have to do even before we get to A. So A in the problem itself asks, what would be the pressure exerted by the carbon dioxide in an 18-liter container at 731 torr? So we know the total pressure, this is P total, but we want to know the pressure exerted just by the carbon dioxide. So we want just the pressure of the CO2. And we know from Dalton's law of partial pressures, the pressure total is equal to the pressure of carbon dioxide plus the pressure of the water. Or another way we can say it is the pressure of carbon dioxide, PCO2, we'll do it on this paper, that the pressure of the carbon dioxide part is equal to the total pressure times the mole fraction of the thing that we want, the CO2 in this case. So the pressure that we want, paper moved over a little bit, is equal to the total pressure times the mole fraction. And since we know both the moles, we can get the mole fraction. So the pressure of CO2 is equal to the total pressure, which was 731 torr, times the mole fraction. So that's the part that is carbon dioxide, 0.43152 moles of carbon dioxide, divided by the total moles, which is 0.43152 moles, plus 0.21576 moles, because that's the moles of carbon dioxide and the moles of water, moles of H2O. So that's the mole fraction right there, which when you add this together becomes 0.64728 divided by that and then multiplied by this, and we get the partial pressure of carbon dioxide equals 487 torr. Since it just said what would be the pressure, it didn't say what units, we can leave it in torr. We could convert it to atmospheres if we wanted, but it doesn't say to, so we don't need to. Number 10b says, what volume of liquid water, if the volume of liquid water can be collected, if the container was cooled and all the water was condensed? Hint, 1 gram of water is equal to 1 milliliter of liquid water, because the density of water is 1 gram per milliliter. It's how the gram was defined, or the milliliter was defined. I can't actually remember which one came first. Anyway, so we have just a conversion for this one. We have the moles of water, 0.21576 moles of H2O. And we can convert from moles to grams. 1 mole of water is equal to 18.02 grams of water. And we also know from the problem that 1 gram of water is equal to 1 milliliter of water. So that will give us the volume, and when you multiply and divide, you get 3.887 milliliters of water. So here's our answer to A, and here's our answer to B. So that's how to do number 10.